So this learning target, this is all about a line of best fit. And it says curve of best fit on your equation. In math speak, lines are curves, and I know that's weird, but don't worry about it. Line of fit curves, and I'm kind of talking about the same thing. We'll see what all this is. We'll see what that is. Fitting a line to data here. So what that is, it's a statistical process. And it tells us, I have a bunch of data. Can I make predictions? It's like being a fortune teller. Can I think about what's going to happen in the future based on what's happened in the past? Fitting a line to data, okay? We use this idea of correlation. And if you kind of break it down, correlation, it's like two things being related in some way. So you've got some paired data. And so you say, oh, I can see a relationship. And we say it's correlated. And we have these kinds of correlation. You have positive correlation and you have negative correlation, or I don't see any relationship between the pairs. Okay, positive, negative, or none, right? I don't see anything. And positive, we call that an increasing kind of relationship, like a line that looks like this. Slope, right? Positive slope, positive correlation. A negative is decreasing, like a negative slope. And then this is we're all over the place. We can't really see it. So if I look at something like this, I say this data is positively correlated. And it says here you hours of study and test scores. So there seems to be a correlation between the number of hours you study and how you do on a test. Would this be a positive thing? Yeah. And it's like what you do is you basically are squinting your eyes and you're like, can I sort of see a line? Sort of see a line. This line has a positive slope. That is a positive correlation, which means the relationship is the more you study, the higher your test score. Now this is a negative correlation because if you kind of squint your eyes, you can sort of see like a line going down, a line with a negative slope. This one is hours of television watched with test scores. This correlation is negative, meaning the more hours of television watched, the relationship noticed was the test scores get lower. So opposite, as one got bigger, the other kind of went down. This one shows no correlation, and I don't have examples here, but maybe somebody was looking at your birth month and your height. And maybe there was no correlation that anybody could find between something like those two pairs. So not everything has a relationship that we can see on a graph. But these two we do. And do these kind of make sense? The more you study, the better you do. The more you watch TV, and I'm not studying, I guess that's what's implied, your test score goes down. I do want to say one thing. Does this mean the more you study, that's what's causing you to do better? Does it? According to that, there is a relationship. But is it possible, it's not necessarily this, is it possible that people who study a lot, for some reason that we don't know, maybe they just somehow have more higher IQ. I don't know. And that's why they do better. Maybe it's not the studying. Maybe there's something else about people who study a lot that's giving this kind of high test score. And by the same token here, because you're watching a lot of television, is that what's causing your test score to go down? Not necessarily. It could be. Or it could be that people who watch a lot of television have some other characteristic that makes them not do well on tests. Or it could also be that it does cause it. But I do point that out because there's this phrase that I like to make sure everybody knows. Correlation does not imply causation. What? What? Yeah, write it down. I'm telling you, write this down. Because, when you watch TV sometimes, or you're reading like a newspaper or a magazine, they will sometimes come out with these outrageous claims. Oh, people who take this vitamin don't get colds. Or, advertising uses this all the time. People who drink Diet Coke, they get skinny. So is it the diet? And so what we do is we see that relationship and we say, oh, Diet Coke makes you skinny. Is that what's making you skinny? I don't know. Maybe people who drink Diet Coke do other healthier habits when they're drinking Diet Coke that are causing them to not be overweight or something like that. So the advertisers are betting on you not understanding this. So kind of have a critical eye. Yes, there is a relationship. It is possible that it does cause these things. However, all this says is I see a relationship in the data. researcher might pursue this further to see if it does actually cause it. It's just saying, is it worth the study? Is basically what this does. So I think that is important. Okay, so in mathematics, now back to math, we have something called a correlation coefficient. And it's represented by this letter R. And there's a whole statistical calculation that's made. And you get a number that's either 1, -1, or any number in between 1 or -1. And based on what that number is, it tells you how strong the relationship is. So something that is perfectly correlated in a positive way would have a correlation coefficient of 1. And something that's perfectly correlated in a negative way would have a correlation coefficient of -1. Now something has a correlation coefficient of 0 to an absolutely no correlation whatsoever. So what I like to say is look at the absolute value of your R. If it's very close to 1, strong correlation. If it's closer to 0, not a strong one. So if you had a correlation coefficient of 0.98, is that a strong correlation or not? Strong. What about -0.93? Pretty strong, but it's a negative correlation. So that's fine. What if it said 0.2? It's pretty weak. So generally, what's strong, what's weak? I like anything bigger than 0.8. It's probably okay. But that's what researchers do. They get data, they perform some calculation, they look at R and they decide how strong is my correlation. Something that has a correlation like this, they're probably going to study further. Something like this, maybe just say, there's not really a relationship. Yeah, here it is. I know I didn't forget it. Correlation does not imply causation. It's just be smart when you're reading things or advertising. Just because there is a relationship does not necessarily mean it causes it without some further research into it. Yes?
Is there a quote from a famous mathematician?
Well, I'm saying it, and that's famous enough for you, right? They all say that. We all say it. It's what we do. Okay, so let's get back to our math now. Scatter plots are kind of easy. A scatter plot is just basically graphic. So you just treat your data pairs as XY pairs. I don't know why it isn't doing that, and that's it all. Stop it. Stop doing it. Okay. So I've got this little example here. What is this thing? This is fish. And I'm looking for a relationship between how long this fish is and how fast it swims. So, I mean, there might be a hypothesis, long fish swim faster. Maybe that's somebody's trying to decide if that's true. So this pipe is almost 38 centimeters long. Here's its speed, centimeters per second. Wow, I would love to see how everybody speed up these fish, but somebody figured out how. Something not as long has a slower number, right? So what we do, visual is everything. It's very hard to look at this. So we graph it. So I'm putting the length of the fish here and its speed here, and I'm just graphing it. So like 37.8 is somewhere over here, and that was 148. 19.2, see, it's just XY pairs. That was 47. 21.3, that's over here somewhere, right? So you see what we're doing? You just you graph those little points, where this is like X and this is Y. Just a question on that. Graphing points. And so you look at it now and you say, wait a second, now I'm looking at my points. Do I see a correlation?
Yeah.
What do you say, positive?
Positive.
Because you can kind of see, if I squint my eyes, it's an upward trend. So I say this is positive correlation, just by looking at that. And this might, tell somebody with the hypothesis that a longer fish swims faster. They've got some, evidence to back up that claim, because they're seeing a positive correlation there. Okay? So the idea is, though, well, what is this line? How can I find that line? And that's what we're doing now. That's the line of fit, the line of best fit. So basically how you do this in a manual way is you make this scatter plot, just like we did here, right? You make a scatter plot, and then you have to decide whether it can be modeled. Does it show correlation? Just like we did here. Yes, it does. Then you say, and say, eyeball a line like, where does this line go? I made a guess. And then basically I'm going to find the equation of this line. How do you find the equation of a line? Oh. Yeah, I find 2 points. Yeah, that I can clearly see, meaning they're right on the crosshairs, right? And then so I'm like, this one's 20 and 75 maybe, and this one, just reading the graph. 30 and 125. And if I have 2 points, can I get an equation of a line?
Yes.
How?
So,
Find slope. Pick one of these points, point slope. And then you get an equation. And now once I have an equation of a line, I can make predictions. What would be my prediction of a fish that's 35 centimeters long? I'm thinking it's going to go around 150 centimeters per second. So you see, so the idea is use data you know to help you make predictions about data you don't know. And that's what a line of fit does. What? Well, and what if it's wrong? That's a good question. We're going to talk about that. Yeah, predictions, statistical predictions, are they always right? Good question, right? So we eyeball this, we just go, that's a bad eyeballing of it. We just did that on the other slide. So I mean, that's it. That's really adding a line of fit doing this. So I've got my little example here for the bird population. We're looking at woodpeckers, as one does. Who knows who this guy is?
the woodpecker.
Who is that?
Woody
Woodpecker. Thank you. Who's heard of Woody Woodpecker? That's it?
Bad child.
Is it an old TV show?
Yeah, he's kind of an old cartoon. But anyway, here's Woody. So, this is what environmentalists do. They want to track these birds. So, woodpecker clusters, I guess they live in little groups. I don't know. And so they're checking them in a forest. So in 1992, they were able to figure out there were 22 clusters. In 1993, 24, and so on, right? Somebody went out there and counted them and found this stuff out. You know what? That's why they are environmental scientists.
I know.
I don't have to do it, because I have no idea how to do that. So anyway, here's what we want to do. We want to make a scatter plot. Now, be careful here. Look at this. It says, use it as the number of years since 1990. Look at my scatter plot. Does it say 1990, 1992 here? No, it says years since. So in 1992 is how many years since 1992? So I'm going to just kind of convert these so that I don't make a mistake and put in the year, because I'm not looking at the years. These numbers are way too big, and they're hard to work with. And it's not necessary to work with such a big number. I'm just going to look at years since that. So make a scatter plot. Now you've got this on your paper, so go ahead and make a scatter plot. This is how it works, right? 2 is 22, so you go 2, and then you're going to have to guess, right? I don't know exactly where 22 is. I'm going to guess. You do your best guess. So go ahead and do that. I'm going to do it too. I made my scatter plot. Now we're still working on it. I got a couple people still. We're almost there, right? Almost there.
I finished.
What do you guys think? So the rules are make your scatter plot, and then look and see if you can see some kind of relationship. Is there any correlation?
Yes.
What do you think?
Positive.
It sure looks positive, right? Okay. Good. So what I want to do is I want to make some kind of line through here that I can use to kind of make predictions and stuff. And I call it eyeballing a line because it's not real scientific. But how do you do that? And well, I got something for you guys. So hang on a second. We got our spaghetti. So what you're gonna do is take that piece of spaghetti gently, right? Very delicate equipment here, and you're gonna lay it against your plot. And you're going to say, gee, I don't know, let me see if I can do this with a line drawer. Where does it go?
Not too big.
So, I don't want that. I want this one. So we're going to kind of draw the best line we can. And again, your goal is to kind of do as many points above as below. And again, it's hard. Just do your best, right? Do your best guess. That was my guess. Let me just get rid of that.
You start bringing spaghetti.
Okay. Everybody's drawn a line, right? So the next thing you want to do, that's good enough, right? You do your best guess. Then you say, okay, how do I write an equation of my red line now, right? The line you drew with your spaghetti. Is you're going to pick 2 points. And again, it's nice to pick points that are right on a corner. Now, what if you're not exactly on a corner? You know what? Didn't you just kind of make up this line?
Yeah.
If it's close, pretend it's on the corner. So I'm going to pick this one. this is 425, that's one of my points. Yours are gonna be different, right? Yours will be different. Do it according to your graph. Your graph, and I'm gonna put this one. I'm doing 530. Then yours will be different. Because are you, shush, are you laying spaghetti the same way I'm laying spaghetti?
Yes.
Well, possibly, but think, how many different ways can I lay that piece of spaghetti down there? Two number ways. I'd be surprised if anybody did it exactly the same as somebody else. Yes, ma'am. Okay, do not take the blue points. See my blue points?
Yeah.
Those are the data points. If they're underlined, maybe. But I am not interested in them anymore. I only want ones on my line. Only on the red line. Now, if it just so happens, well, there's one on there, okay, but you're not plotting a blue point, you're plotting a red point. I want the line only. Is that clear? Don't pick random 2 points here. I just want to emphasize, so everybody's quiet right now. Everybody's quiet right now and listening. Do not pick 2 random points up here. That is not how it works. Because if you do that, what if you pick these 2 points? That makes the line of fit this. Is that a good line of fit? No. You want to draw the line, 2 points on the line you drew. Is that clear? Okay. Then you write down the coordinates of those points. Yours are probably different. That's okay. Then I have to find the slope, right? Isn't that okay? So mine is, slope is, mine is 30 minus 25 over 5 minus 5. I got a nice number, didn't I? I got 5. Now you may not have that equation, and that's okay. You may not have that slope. Find your slope. Find your slope. You're not doing it, okay? Write down 2 points on your line. Okay, that's my slope. Now for me, here's my slope. I pick one of these points. I'm picking this point. Doesn't matter. Y minus 25 equals 5 times x minus 4. Yours will be different. So this is what I got. Y equals 5, x equals 5. So go and figure out what your line's equation is. It won't be my line, it'll be your line. Your line. So once you have an equation for your line, I want to hear what it is. What's the equation for your line?
I got it.
What did you get, Ben?
I got y equals 2x minus 1.
2x minus 1?
Yeah.
Okay.
Y equals 5x.
That's it? Full stop? Okay. Yes?
I was like, on the test would be
Would what?
would they vary?
Of course they will. Right, why is yours different than his from mine? Why are they different? Because
There's different ways to do it.
there's different ways to lay a piece of spaghetti.
Oh, I got it.
I got Y equals
Somebody else have one? What'd you get?
Y equals 18x minus 14.
18x plus 14. Something's not right because 18x is a very steep slope. If there's possible there's a mistake there. So try it again with your slope. It sounds a little bit.
I got it. 5x plus 33.
I got y equals 2.
That sounds pretty. That's how you up here.
Is mine good?
So I'm wondering if there's a mistake. You do want to kind of do a sanity check. Because that puts your line up here. It doesn't look like you hit your points. There's probably a mistake.
I got y.
Yes.
I got
Please throw out that gum. No gum in this room. Get rid of it. Get rid of it first. I guess you have one?
Y.
10 thirds x plus 15.
I got
And that's an interesting one. 10 thirds about 3 point something or other. So we're actually pretty close. We're not too far.
my line. Wait, how do you find the line?
I got it. Y equals 10 thirds. 10 with x plus 15.
No, you got it.
Wow.
No, you didn't. Yes.
I got Y equals 502x.
It's down a little bit, like 45 meter from my stuff. I think there's a mistake. So, this puts you over here. So it should make some sort of sense.
I got Y equals 7.
I changed it. I got y equals 5x plus 5.
Okay, that's way better. So what you want to do, shush. Okay, so it needs to make sense. Now, I think you have a better sense of what's going on here. What is this little squiggle here? What is that?
Is there a
That means
zero?
That means
it's
it's the
data.
cut.
It's like,
It's a break, it's a break.
everything below 20 is the.
It's like we cut the
It's a
graph
break.
off.
Yeah.
We cut the graph off. So instead of making this unnecessarily long, so be careful here. One way to do this is to look for the y-intercept, because that's an easy way to write a graph. If it's got a little squiggle, I can't tell where it's going to be. But I can sort of see if this was 20 and 15 and 10, like I can see about where it's supposed to be. So I'm thinking numbers like 5, 10, those are good numbers, and 15. If you're getting numbers way up here, you made a mistake. So do a sanity check. If you're not getting something that looks like this kind of, if you've got an 18 for your slope, I mean, that's up here, it can't be. So again, make sure your line makes sense. So that would be a line of fit. Now what would be a line of best fit? Now each of us having like 16 different answers, like, wow, is that good? And maybe it's good enough, it depends what you're doing. A line of best fit is the best way to lay that piece of fit down. And how many best ways are there?
A lot.
There's one best way. One. So we need to find that one best way. Okay. Yeah, this tip is actually a good tip. This, again, repeating, don't use any of these data points. Just don't take 2 here. Draw the line. Take them from your line. Okay? Now, if you can use the y-intercept, use the y-intercept. Because remember, you're going to calculate a slope. If you can see what the y-intercept is, that's the easy way to write a graph. Right? You just plug that in. Because I couldn't see my y-intercept, I had to use point slope. So just keep in mind, always look to see, is the y-intercept easy to find? And use the easy way, because it's error prone to write these things. All right, so the eyeball method, again, is not very mathematical. I want to fit a line here, and look at this. Because when I do something like this, interpolation is saying, well, what would it be exactly at, say, 7.5 years? So I can figure out almost exactly a really good guess. But what if I want to know in the future? What if I want to know 15 years from 1990 what a prediction will be? We call that extrapolation. We're going to be way up here. So that's why we want these lines. Okay, whoops. This is how you find the line of best fit. Okay, here's the equation. So you want to find slope. N is your number of points. You're going to add together the sum of all the points multiplied together. You're going to subtract the sum of the x's times the sum of the y's. You're going to divide by n times, again, number of points, the sum of your x's squared minus the sum of all the x's squared. That's going to give you m. And then if you want b, it's the sum of all the y values minus m, the slope, which you got up here, times the sum of all the x values divided by the number of points. Correlation coefficient is handy. Here's what you do to keep that. Okay?
Yeah.
So you up for that?
Yeah.
I got some bad news for you. We're manually finding a line of best fit. It's just out of scope for what we're going to do in this class. I'm really sorry. I know you were excited to use this formula.
I wanted.
No. You can if you want.
I want to
Yeah.
use that formula.
We're going to use the calculator.
Thank you.
You're welcome. I am going to give you a copy. Okay. Linear regression is, excuse me, are we ready? Linear regression is the statistical name of finding a line of best fit. Linear line regression means, finding that line that fits data. So here's what you do. You're going to use the calculator, and you're going to put the data in 2 lists. So, you know what? I guess we can do this. So you press stat, and you press edit. Remember, we've used lists before. So all the x's. So like the other case where we were doing what, rotation length versus the speed, you would put all the lengths here and all the speeds here. As you read across, you should see XY pairs. So if something was 20 centimeters long and it did 25 centimeters per second, they would be across from each other. They match up. Okay, so I'm just going to put anything in here just so I can show you the steps. And I'm just putting any numbers in. You can too if you want.
If we do the one that's on the
We
sheet.
will eventually, but I just want to kind of walk through the steps a little bit. So you put points in. That's it. Then you perform linear regression. So you remember stat calc, right? So stat calc. Before we use one variable statistics, right? Gives you averages, linear deviation. Look down the list here. Do you see something that says lin red? That's number 4. Linear regression. And look here, it says AX plus B. Now I know that's an A, because then that was regression, and as long as your x's are in L1 and your y's are in L2, you can just press enter. Now, if you have like a TI-84 plus, there might be a little menu there, but I think you can figure out where to put everything, right? I hope. And so if you run it, quiet down. Okay, it's telling you, here's the format. Y equals ax plus b. A is 1 and b is 3. So what would the equation be? Y equals 1x plus 3. Plug them in, or y equals x plus 3. That is the line of best fit for those data points. You were to lay your spaghetti perfectly on that statistical plot, that little plot you did, it would be perfectly that line. Okay? Does that make sense? That's the easy one. And it could be all you need. Now, the hard way isn't that hard. What the hard way does is it allows you to put the equation into the graphing. And let me just show you how that works. So you do a stat calc WinReg, just like you did before. And then, okay, it's vars. Say vars, just watch. Vars, you move over 1, 2 y vars, so function here is lit. You press enter. When you press enter again, I want it to say y1. So see how it looks a little bit different now? And then I press enter, and nothing looks different until I go to y equal. It automatically puts that graph in here. And what's really cool is if you look above, I'm trying to look, see where it says graph, and look above here where it says table. If you press the second button in graph, these are all the XY pairs that go. So if I want to make a prediction, well, yeah, you put in some data. What do I predict is going to happen when x is 6? I predict y will be 9. So you can use these little tables to help you make predictions. We'll go over it again. We will go over it again. But those are kind of where we're heading with this. The correlation coefficient. It is helpful to see that thing too. So on some of the calculators, the only way I can figure out to get there is through the catalog. Where's the catalog? You see your 0 key? Look above there. See catalog? So you press second and 0, because we have to turn on what we call diagnostics, statistical diagnostics. So I want to get to diagnostic on. What I'm actually looking for is where D is. So you're going to press, see where it says math, the button below it? There's a little D in green. Mine is green. It's matching the color of my alpha key. It automatically has me in alpha mode because I see this little A. So if I just press that key, it's going to position me close to where I want to be, which is diagnostic on. And turn that on. It's 2 enters because I want to see that word done. So watch what happens when I press my WinReg again. Stat calc, linear regression. I'm going to do the easy version now. I get this R equals 1. Wow. Is this good correlation? Is it positive or negative? Now we'll talk about R squared when we do quadratic regression. This is correlation for R. Right? Okay, so let's do another example using this. And so we're going to just repeat these kinds of directions. You see it several times. Yes, sir? Do you have a question? No? Okay, so now if I want the line of best fit for my woodpeckers, yeah? So now I need to put this in my calculator. So again, this is 2, this is 3, right? All these numbers. So in your calculator, you're going to go stat, edit. We're going to clear out the junk that we had before. Clearing it out. So I'm going to put in what? 2 through 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are all the X values, right? Those are the year since 1990. I'm just trying to see. In L2, you kind of put the right click over, and I'm going to put in these numbers. But they have to match. So where I put the 2 in the same place, so I got 222 here. Put in all the Y values that go with it. Always takes me a long time. Anybody have a question what I'm doing here? Do not know what I'm doing? And everybody is doing this, right? Everybody doing
I'm
this?
not doing it, I'm just watching.
Well, you should be doing it.
Wait, for the X, should we go to, for the X, should we go to 10?
Well, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you should have an equal number in L1 as you do in L2, because these are ordered pairs, right? Yeah? And then check. Check, you didn't make a mistake. I make a mistake all the time with these. So 222, right? 3 is 24,
Yeah.
4 is 20. So I'm checking that I put my data in correctly because if you make it wrong, it will be wrong. I think it's okay. I think I got it. Okay?
Wait, then you put.
All right, now, so it's in. So watch what happens now. I'm going to go stat, calc, linreg, and if I just want the equation, hit enter. Whoa. Round to the nearest hundredth unless it tells you otherwise. What's the equation? Y equals, A is 3.7x plus B rounded 12.47. So Y equals 3.7x plus 12.47, and we should all get that. Now, my guess was Y equals 5x plus 15. I think it was, or 5. Not too bad. But this is best. This is the best way to lay that piece of spaghetti down. Okay, now, let's say, now look at my correlation coefficient. Is it a strong correlation?
Yes.
Yeah, it is.
How did you get that? How did you get the correlation to show again?
You go to catalog, right here, go to your catalog, which is second 0, find command diagnostic on, press enter, and then press enter again till you see that where it's done.
I put it in the thing.
Okay, let's say I now want to make some predictions. I'm going to put it in my table, so let's review how you do that. So, stat, calc, linreg, which is number 4. As long as you're using L1 and L2, you can just hit bars, go to Y bars, which is one to the right, function, hit enter, Y1, hit enter, it's here. You're going to run it again, if nothing looks different, until you go to Y equals, right? It's in here. It's in here. I like looking at the table. So now if I wanted to know what's going to happen in 2001, well, that's 11 years since 1990. So I go to 11, and that's about, we expect to see about 53 clusters. It's a guess, but it's a guess based on statistics. Which brings back to your question, is that always right? I don't know. Maybe there's a forest fire, there's 0. I mean, we don't know. We make our best guess based on what we know. Now, if I want to predict what's going to happen 20 years, like I got to go all the way out here. Almost 83 clusters more than that. That's 19. So, 10 more years later, 87. Is that going to happen? Now, the farther you get from your data, the less likely that it's going to be good. Okay, the less likely that it's going to work. So, we do our best, right? But we also realize that once you kind of get past your data cluster, it may not be as correct, but it's our best guess, right? Statistical guess. Boy, was able to get through that. Okay, good.
I put it on so it wouldn't come up.
Okay, if it didn't come up, you probably made a mistake somewhere. Check your data. Check your data. All right, we did this chart here. So there's other things we can do. Let me see. I just want to see the other one. We probably don't have time for this one. Basically, what you would do is I want to find the line of best fit. Line of best fit is that calculator activity. So what you would do for ones like this is you would say year since 1990, say, or year since 1990, even better. So you make a guess, or you can write what they are. This would go in L1. This would go in L2. You run that linear regression, and then you make your predictions. If you have trouble remembering the bars thing, just use this equation. What's going to happen when x is 20? Just plug a 20 in here and find your y. You don't have to use the table. It's just to make things easier. What's your question?
Change the year.
It said, you do what it says, year since 1990, don't put the year in. What happens is sometimes the years are so big it blows up the calculator, so the data's too big for it. So use what it says, year since something. You'll get the same values. What else is important? Zero of a function, that's kind of an important thing. Where is that? Remember a zero of a function? What is that?
The y-intercept.
The x-intercept.
X-intercept.
Oh.
That's y equals 0, right? So if I find a zero of a function, like for this, somewhere the active clusters were 0. And I'm just going to kind of scroll through my calculator. And I'm looking to see when y is 0. Whoa. Somewhere here, between -4 and -3, and it's year since 1990, so I guess that's like 1987 and 1986, I had 0 clusters. So, does that make sense? Does it not make sense? What about if I go 6 years before then? I had negative clusters? Huh? So again, you always have to kind of pay attention to what makes sense. What makes sense with your data, okay? So I think we got there. I think we did most of the things we need to know here.